Hello everyone, my name is Mohammad Hassan and I am a PhD student here at Federal University of Ouro Preto. Today we are here to represent our paper titled as a framework to develop a cost-effective charging policy framework. So now let's move to the presentation. So here is the title of our paper. We are here to represent a theoretical framework to reduce the total cost for the electric vehicle. So here is the agenda for today's presentation. So the environmental pollution is affecting the transportation system because of the fossil fuels generated by conventional vehicles. That is why electric vehicles, the EVs, are receiving considerable attention in the smart cities. So that is why we are here to overcome this issue and provide reduced and more flexible total cost for the EV users. As the demand for EVs grows, it becomes crucial to optimize charging strategies to ensure cost efficiency for the user convenience as well as for the environmental sustainability. So far we have seen some authors have discussed about partial charging, dynamic pricing and V2G integration or some station placement methods. But the limitation that we have seen here is that authors ignore the real-time traffic or topography effect. So the problem statement and motivation for our paper is the range anxiety and charging inefficiency which hinder the EV adoption. We have considered these 4 points or parameters: traffic, which is denoted by D, energy consumption, which is denoted by E, charging prices, C, and topography effect, H. So the goal for this research is to minimize or reduce the total travel cost, which is indicated by TC in this research, through adaptive charging decision. Charging decision are the rules which we have defined in this research and is denoted by CD. Let us consider this is an instance for a network that we have considered in our research, where N0 denotes the starting point and N10 denotes the ending point. We have considered 9 different charging station positions starting from N1 to N9. So as you can see, on each station there are some values defined on each station, like traffic on the specific route, the energy which is required for a vehicle to go from one place to another, the topography effect which is on this specific route, and C is the charging price offered by each station. The workflow for this framework is, at each station it will compute the ATC, adjusted total cost, based on the mathematical equation that we have defined. Then it select the lowest ATC, which would be the best ATC to go on the next station. Then we apply some dynamic charging decision CD rules based on 0 to 20 scale to bypass or partially recharge. So here is the core idea of our theoretical framework. A vehicle should decide whether not to charge or charge at a specific value. Charging decision scales. We have defined these CD levels in our theoretical framework. For example, CD1 denotes to charge a vehicle up to +5 scale. CD2 defines to charge a vehicle up to 10 scale. Similarly, CD3 up to 15 and CD4 up to 20, and finally CD5 means not to charge at this station and the driver should bypass this charge and go on. The adaptive logic for this theoretical framework is it should increase the charging decision level if the traffic is greater than 10 or the topography effect is greater than 10.
So these are the rules that we have defined in this research, where a user should decide not to charge and bypass the station or to charge at a specific level.
So here are the dynamic programming setup of our paper. TC is denoted by total cost and it is defined by equation 1. The total cost would be calculated by incrementing by the addition of energy required from station I to J, the traffic between I to J, and the charging cost offered by the station. We calculated the ATC, adjusted total cost, by equation 2, which is represented here, and where the ACJ is the adjusted charging cost from CD decision. Once the equation have defined the CD decision, then we calculate the AC, this adjusted charging cost, and we put this value in the equation 2 to get the ATC. Similarly, at each point we will define and we will find out the value of ATC. Once the value of ATC is lowest, so we should consider the lowest ATC to go on to the next station. It should be noted that at each station CC, the current charge new should be recalculated, because once the vehicle have recharged its vehicle, then on to the next station it must consume the energy and it should be subtracted from the previous charging value. So on each station CC new will be calculated in this format as defined in the equation 3. So we have defined some baseline solutions to compare with this tech framework. Now, the number one is LDR, least distance routing. So in this solution, a vehicle should find the least distance station from its current position and go to that station and recharge there. According to LDR, as defined the values in table 2, the total cost have been computed as 167, and the route selected by LDR is N1, N2, N4, N6, N8, N9 and N10. These values are computed with the help of equation 1 as discussed in the paper. The second baseline solution is the LCR, which is least charging cost routing. In this case, each vehicle should consider the least charging cost offered by each station. So wherever it finds the least charging cost, it will go to that specific station and recharge its vehicle there. According to LCR, the total cost TC has been computed as 129, and the route which is selected by LCR is N1, 3, 5, 7 up to N10. So for the simulation steps, we have used Sumo simulation of urban mobility software, and we have run this for 1000 vehicles, and we consider the Tapas colony map of Cologne for this figure as it is shown in figure 2. So here is the map for Tapas colony scenario, where the rectangle N0 shows the initial point for a vehicle and N10 represents the final destination. The green line here represents the route selected by our framework tech. Here are the values which we have considered in this scenario. We found these traffic values on a real-time situation by using Python script in the Sumo simulation. Then we normalize these values between a scale of 1 to 20. Similarly, the value for energy required from going from station I to station J were considered this. Then we normalize this value up to scale between 1 to 20. The charging cost offered by each station were chosen randomly. Similarly, the topography effect values were chosen randomly. The TC values are considered as a naive approach, but we have defined ATC that a vehicle should consider this ATC for recharging its vehicle. So here are the results, the route selection and cost performed by LDR. This table represents the performance of LDR, which is, for example, on this specific instance, from going N1 to N10 is 167, where LCR is gone for 129 by following this route N1, 3, 5 and 7 and N10. Here is the route performed by tech, and as you can see in the figure, this is the route N1, 2, 4, 6, 8, 9 and 10, and the total trip cost adjusted by tech framework was 114. So clearly this tech framework outperforms the both naive approaches from 12 to 32% in a manner of total cost. So here is a conclusion. We developed a theoretical framework for EV charging policies using simulation based data. So the core area, the core goal for this research was it should be considered a large scale network where an EV driver needs to recharge its vehicle by several times. For the future work, we will be defining the stack on some highway networks, and that's it from our side. Hope to see you guys next time in a person. Thank you so much.